Hi, today I would like to talk about the final project of a computer science section from the Odin Project, which I just finished. Actually, I finished it yesterday. It's called Travails. It's about finding the shortest way uh, of moving the knight on a chessboard from the start point to end point. And the assignment says, now that you are pro with depth first search and breadth first search, let's try using our search algorithm on a real problem. Yeah, here's the chessboard. This is just a preview how it might look like. Yeah, so if the knight stands, for example, the 2D array, which is chessboard, on a field 3-3, the available moves from that field are 4-5, 5, 4, 5, 2, 4, 1, 2, 1, 1, 2, 1, 4, and 2, 5. I hope I haven't repeated myself. Yeah, so knowing that, we have to find the shortest way from one point to another. So the output should look like this. This is the input, this is the start point, and this is the end point. So the knight should move from the point 3-3 to 4-3, and it has to find the shortest path. What is the shortest path? The shortest path will contain as less steps as possible on its way. Chessboard is a graph. What kind of graph? We have different graphs: weighted, unweighted, directed, or undirected. Let's analyze it. I think, okay, can I use my drawing pad to show you something? When the graph is directed, like this is the node and this is one node, so the edge, which is just a connection between one and another node, it goes in one way. So when it goes both way all the time, so we can say this undirected, because we can go from the A to B and from B to A, like this, for example. When it looks like this, I think this is direct, because we cannot go from C to A, for example. And for each field here in the chessboard, we can go whenever we want, and the only constraints are the formula of movement of the knight, which is very specific, and the edges of the chessboard. Yeah, so the knight cannot move, like, for example, here, yes, because this is how the knight moves. It moves, for example, up two fields and one field right or left, for example. It might as equally move left as right, or here, like here, but now we're going beyond the chessboard. So those are our constraints. For example, from this point, yeah, the only possible moves are here and here. Yeah, we can move like this or like this. Came to the conclusion this is unweighted graph, so I have to find a solution for unweighted graph. So I find out about the algorithm called Dijkstra's algorithm. Heard about this name from time to time when I was watching YouTube videos or other resources, and I just remember that because of the fancy name he got, and the guy Dijkstra. Firstly, I thought this guy could be or can be a Russian or someone, but no, but it occurred he was a Dutch guy, and what he invented, he came up with the idea algorithm to find the shortest way between the nodes. For example, between the cities, he came with this idea as I read in a book, We Programmers, written by Uncle Bob, the Uncle Bob, Robert C. Martin, and he didn't even draw anything or handkerchief or nothing like whiteboard anything. He just came up with this idea in his mind because it was so simple. But sometimes the simplest ideas are the best. And just by following the nodes and measuring the weights of the nodes, we can find the shortest way to the final node. For example, we want to go from this node to, for example, here, which, for example, this is the graph, circle graph, yes? And yeah, so following this path, for example, here, we have to add each weight of single edge together, and the result, if it's bigger than the result here, for example, this we got here, so the result of following this side of the graph gives us 5, and here 4 plus 8 plus 4 is 12, plus 5 is 70. 70 versus 5, it's pretty obvious. This is the shortest way. Yep. Actually, I was trying to draw an arrow. Yeah. So yeah, let's stand with this. We don't have any weights here. So what are the alternatives there for Dijkstra's algorithm here? I think maybe we can apply Dijkstra's idea, and I'm saying we cannot do it, that this is not impossible, but I think this is not the most, how to say it, proper way to do it, or yeah, most effective, efficient way to do it. So the solution might be breadth first search. Yeah, I came up to this later on. When I show you the code, everything will be obvious to you. Okay, let's get to it. Show you the VS Code. Actually, I'm not using VS Code. I'm using VS Code. This is the big difference. Okay, first of all, we have to start to find edges, which are connections between the nodes. So for each, what will be the node here in our graph, which is the chessboard. Each field is a node, and those nodes can, they will be nodes, the objects, yes, because each node is most often object. So objects can hide something, some properties. For example, when I started to thinking about the solution of this problem, started to mindlessly put as much information to the node, which back then I was thinking it might be helpful in the future. So I put to the node, for example, coordinates like X and Y and the values, because I thought maybe values can be helpful in the future. The value here is the number, the row of each chessboard. Like this is the 0, this is the 1, 2, 3, and so on, so on. 6, 7, yeah. I cannot count. So, but the most important, the property of each node is its moves. I have hidden here the possible moves for each node in this array. I call it moves. So, what are the possible moves for each field are hidden here. Yeah, and for example, all of these 8 moves are gonna be stored in this moves array. For example, for this 0, 0 field, the possible moves will be containing only 2 nodes. This one, 1, 2, or 2, 1. It's gonna be stored here. And this is the property for visited nodes. Yeah. So when we're gonna follow the path, we don't wanna make any circles. Go back to the fields which we already visited along the way to the endpoint. I started to think about the board as a matrix. So matrix to the array, aka matrix. I like to. There are many people who hates making class in using class in JavaScript. I don't know why. I think it is very helpful. Yeah, it's straightforward and it's easy and it's very simple and makes it clear to read the code when you're using classes. Actually, everything is object in JavaScript. Yeah, 8 times 8 is 64 fields, 64 nodes. So for 64 nodes, I had to create a matrix which automatically will add for each node, will fill its array of moves with other possible nodes. I hope it's not it's clear what I'm saying here. And I have, okay, this number of fields. So number of fields equals 64 because size, power of size, power of 8. And the matrix. This is the in method which this class will use on itself. So it's referring to the first instance of the matrix, and while it's gonna be created, it will use that inner method, and based on the size, it will fill it with nodes. So it will use the node class to fill this 2D arrays. Coffee time. And it returns the matrix. So we can use it later on. Based on the coordinates, we just return the single node, and here adding edges. Yeah, the class doesn't use it on itself automatically. It uses it later on. Here, when I assign the new matrix to a variable, which is called board, and later on I had to use this method on the first instance called add edges. Two arrays called factor x and factor y. It contains 8 factors because there are 8 possible ways the knight can move. So starting from this point, first I have to clear this. Yep, this is the one. So the x axis will decrease from this point -2 because knight will virtually will go here. So the x will go x -2, and the y-axis will go +1. We got the first move, so this is the one, and we'll have to find another. This is the 2. Second possible move. How? Of course, the x-axis will decrease by 1, and the y-axis will increase by 2. So we got -1, -2, and so on. So out of those 8 moves, we got only 2 possible. So the 6 of them are cut off because of the constraints. Yeah, this is 8, but in this case, the size equals the length of the one of the arrays, actually both of the arrays. But if possibly this 2D array would be bigger, the size variable would be no longer relevant. So I think this is not a mistake because it works for a chessboard, but it wouldn't for in the other scenario. So I think I can easily here change the size for a factor x length. Factor x length. Yep. Here and here and here. But coincidentally, the number of the possible movements for a knight equals the size of the length of the one side of the chessboard. So for a node and his array of possible moves, it pushes each time and temp matrix. Temp matrix is the matrix itself. So the coordinates of each node, the res x and res y. So it pushes each node of this coordinate to the possible moves for each node. I guess one of the arguments is no longer necessary, like this. And here I use the function itself. This is just a prototype of the function, and here I use the function. Okay, 2 arguments, start point and end point. First, I've wrapped it in the try. So, for example, someone will put, type here something that goes beyond our constraints, like 9 or 9. As we know, the limit is here 8 and 7. Yes, because the index starts from 0. This is the constraints we got, but for example, so someone goes beyond that, or the values are below 0, it will throw an error. Catch event based on this if statement to inform the user that for example, the first wrong coordinate he used was wrong. The coordinate cannot be lower than 0 and bigger than, for example, your coordinate. Yeah. algorithm most commonly used data structure is queue. So first in, first out, FIFO model. Yes, we are checking if start node is end node. But before that, we're checking if the queue, if something is in the queue. So if the queue exists, there's nothing in the index 0, the queue is empty, the array is empty. This is my favorite and shortest way of checking this. We move the knight and we have to record that field in the path, because later on we have to recreate that and output it, all the nodes we visit. So we use the method, array method, shift to get rid, to extract the first element from an array, which is the start node. And we put it in a path. The path looks like this. Path contains only the start node, yes? The path only start node. So right now we copy this and assign to the node. That's why it's because otherwise when I would use pop or shift, it would change the array itself. So I would cut off the element and make the array empty or shorter. If node equals end node. Okay, let's leave that for later on for a final case and move on here. This is the most, those are the most important lines, I think. For const move of node move. It's a for loop, for off loop actually, not for in, because for off checks the value of a property if it will be for in, for example, and we would iterate through the properties of an object, it would return the name of the object. And that's why I think I should change here with my level order implementation for off, yes. So it iterates through the possible move of single node, and the node is taken from a path which is taken from the queue. you know the drill, and the node is not visited, we mark it now as visited, so we change it the boolean value for true, and then we push to the queue all the values we had in the path. That's why I'm using here the spread operator, because it extracts everything which this array contains and add another move here. So it remembers the past, and it's added to the past this another move, so we can pass it to the another node. That's how we create this path. A second to last node becomes the last one, so they have the same values. Okay, they are the same right now. We now here the log, you made it, because this is how the output should look like. You made it in X moves. Here's your path. Yes. So I created here an array. I push it to this array, and the element is actually the property of the element, which is the footprint. And the footprint is the property of a node, which is exactly here, the X and Y. I got X and Y here as well, but I created footprint especially for that purpose, so I can easily put it to the result array. And for each element of this array, I log each element, which is already each footprint. And yeah, so I just name it MGS as a module and use it node to actually run the program. Simple as that. Here's your path. 0, 0. Okay, let's follow in the real time where it goes. First, we start with 0, 0 field. 1, 2. Yep, it covers with the previous option. 0, 4. Okay, it has chosen this way. Why not? Still the the least amount of moves, so it is the shortest way. 1, 6. It goes here. Next, 3, 7 goes there. 5, 6, and the final here. So the path is, let's change that, maybe blue. Yep, got it. Winner! Win! Yeah! Got it. This is pretty much it. The idea is to iterate each time X and Y has to be closer to the goal X and Y for each iteration. For example, because when I reach, for example, the X axis and my end node exists on the X axis, it shouldn't change it. It shouldn't do anything with the X any longer. It should stay on the X axis and just follow increase or decrease the Y axis. Okay, so I'm gonna get rid of this. For example, not much will change here, I guess. What's wrong here? Okay, while. Get rid of the while. So each time, if temp x is less than node and x, it should increase the temp x value. Temp x plus plus. Yes, that's simple. And in different case, else we got else if temp x is bigger than and node what happened? What the hell? Just wanna type end node and node back. Yep. Okay. Else if, because if it's equal, it will stays the same. Nothing will happen. Else if temp x decreased, if it's bigger, and if it's equal, then the else case will be implicit. So I will start right after this checking the y-axis. Temp y is less than and node. No, I'm tired. Then y increase this, and else if temp y is bigger than and node y, then temp y will decrease, and nothing will happen if it's the same. And just right after that, I will change the two properties x and y of the current temp node are increased or decreased, depends. So now I have to extract from the matrix the node which has the same x and y. So I have to use get node method, get node method from the matrix, from the board. Yes, so I got the board. So the new node, yes, let's call it move. Move equals board board get node with values of temp x and temp y. So this is just the argument x and y. It's gonna find from the board and let it move. Okay. So move will be next temp. Yes. Okay. So I don't have to mark that the temp is visited. I'll just go further. So temp equals move. But I have to leave the trace. So I have to put something in the path, push something in the path array. So path push push footprint of what? Of move. So do it afterwards or in the beginning. No, after path push. Afterwards maybe. I got push here. Temp footprint. Yes. And we'll return the path. Let's say it reaches already. Okay, checks. This is right while. Okay, so it goes out of the function and it's returning the path. If it's not decrease or stays the same, for example, if the x is the same, so nothing will happen. I'm very curious. Okay, first attempt. 0, 0, 10, 20, 30, 40, 33. Let's check it out. If it goes diagonally. Yeah, okay. Let's swap the order. What's happening? Interesting. Infinity loop. Got a problem here. Something's wrong happening here. When we start from the bigger value, the field. Oh, okay, let's debug it. While if else, if let them push them path. Okay, debug console. Run it. What is the path here? First, 3 is correct because we started 3 temp x, start node. Which is the temp actually here? I have to look here. Which is the temp? Footprint 3. Okay, let's go further. Temp y slash the end node. Speaker. Let's go 3, 2. Temp move. Let's check the temp. 3, 2. 3, 2. No, should be 2, 2. Why? It's X. So nothing happened with X. Temp X, X. Ah, yep, got it. Got it. I got it. Got the bug. Run it. 2, 3, 2, 2. One more. One more. Who knows? Who knows? 2, 4. 2, 4. From 0, 0 to 2, 4. 2, 4. Yes, yes. Okay. 0, 0, 1, 1, 2, 2, 2, 3, 2, 4. Speechless. Speechless. I'm too tired to even to be excited.